So once again, you are all welcome. We have been dealing with this data set, the one you see on the screen. We've been dealing with it for some time now. And this data set is what we've been using. Okay. We've been able to learn how to use DEA to generate this frontier, from which you are now able to assess the relative efficiency of every one of the DMUs by radial means, okay, by proportional reduction. In this case, an input oriented, so by the proportional reduction. And on the basis of this, we've been able to learn how to estimate the technical efficiency under CRS. We've learned that, okay. We've done that, taking all of the time. We've learned how to estimate the technical efficiency under VRS, how to identify the scale efficiency. I didn't mention it fully, but we indicated how to get the slack-based measure. Now, if you look at the slack-based measures, you can see that on average, they are usually lower than the CCR or the BCC model. And then this section returns to scale at the firm level. Okay, you've learned how to do all of that. Okay, so that's what you see in the middle section there. Okay, so please note that we've been able to go through all of these. What we want to know today is the non-parametric global test of returns to scale. Okay, we want to determine the returns to scale at the globe, at the global level. And that's the essence of today. Now, anytime you are doing this in your thesis, you have to indicate to the reader why it is important to do this. It's important, okay, to make a statistical testing of this returns to scale underlining any technology. Why? Part of the reason is because, you know, the type of returns to scale that you assume can lead to the results different from the results you will get had you assumed a different returns to scale. So let's say that you assume that the firms are operating under constant returns to scale, when in reality, they are operating under variable returns to scale. And now you're going to use variable returns to scale to do your analysis. You get a result that is significantly different from if it was a constant returns to scale. You'll be concluding based on a wrong underlying technological assumption. That's how it be. And when that is the case, that is not good. Most of the authors you see here, okay, Zhu and Sayford, Keston and Yukot, Nip et al., Podinovsky, and above all, Simar and Wilson, all of them have indicated this returns to scale situation. So please know and understand why it is important to undertake this returns to scale. So a typical example is that let's assume that the industry is operating under VRS, or the industry is operating under CRS, and you assume that it's rather operating under VRS, okay, you're going to overestimate the technical efficiency scores by the scale efficiency. Okay. So it's important to know. And we've always been saying that constant returns to scale is only feasible when the scale efficiency is at unity, or is 1. So let's try and get into the statistical underpinnings of the returns to scale assumption. Okay. Let's try to do that. The first thing to note is this. Banker, okay, and this is the same banker who projected the BCC model, Banker, Chance, and Cooper. In 1996, Banker alone proposed semi-parametric tests of returns to scale. And these tests use Kolmogorov-Smirnov test. Okay, this is kind of one sample test where they made some assumptions that are quite dubious in the language of Simar and Wilson, or they are uncertain. And so Simar and Wilson in 2002 postulated a bootstrap test of returns to scale. And that is what we are going to use to do the testing. The idea is to use that test to determine the presence of scale economies So you can use that to determine the presence of returns to scale at the global level, but even also at the local level. Now, at the global level, the global returns to scale assumption, you got to make your hypothesis. The null hypothesis says that the technology is globally CRS. That's what you see on the screen there. And the alternative is saying that the technology, that is a technology set, is VRS or is not globally CRS. So this is the null and the alternative hypothesis. How do you test for that? But before we show you how to test for that, remember how the VRS graph was. So remember, this time we're not looking at the returns to scale at the fair level. No. We are looking at it at the global. So global, you are going to just consider all of the ones on the VRS, or it's going to be for the NIRS, or it's going to be for the DRS. Okay. So that is a situation, but you don't need all of the 4 different ones I taught you. You don't need all of them. You need 3 different ways of assessing the efficiency, the CRS, the VRS, the NIRS, okay? And then you do that. Now, the null hypothesis says that the technology is globally CRS. Now, if the null is rejected, it means that the technology is not CRS everywhere, but it is variable returns. And so you are going to now go to the next test, okay? The next test, which is much more less restrictive null hypothesis. Now, what is that next test? Well, remember, now you are saying that it is VRS. So you go and check between, you're going to check between the null hypothesis of CRS and NIRS, non-increasing returns to scale. Okay. And when you do that, you can now make your conclusion. According to Simar and Wilson, okay, what they did is to propose a set of related non-parametric tests of returns to scale. And as indicated, DS is based on bootstrapping, and they generate a test statistic. The test statistic is S. And what they did is that they created 3 different test statistics, which are ways of analyzing the returns to scale. Now, Simar and Wilson, 2002 paper dealt with 2 of them, and then Simar and Wilson, 2011 paper dealt with a 3rd one as well. Now, the first one, which is the S1 cap, is known as the mean of ratios. You're going to see the formula very soon. The second one is known as the ratio of the means. Okay. Ratio of the means. Now, let's look at the first one, the mean of ratios. So if you look at this thing very carefully, once you find the CRS, okay, this is an output-oriented measure. So once you find an output-oriented CRS scores and output-oriented VRS scores, then you will use the summation symbol to be able to generate this statistic. So this is a test statistic that you're going to generate and compare it with a critical value and then make your conclusion. That's the S1. The S2 is that you don't have to divide them before you find the summation, but you find the summation before you divide them. Okay, that is a mean, the ratio of means. Okay? So that is the ratio of means. And that is a statistic number 2. The 3rd one, and please know you are going to do all 3 of them in your work. The 3rd one is the one I said was proposed by them in 2011. Okay, what does that do? Well, that one, what they did is that they developed that test to be known as the mean of ratios less than 1. The mean of ratios less than 1. So you can see, remember the first one was known as the mean of ratios. So let me just go back. The first one is known as the mean of ratios, the S1. Okay, but if you look at the formula 1 and formula 3, the difference is that it's the same as the first one, but this time it's less than 1. So it's a mean of ratios less than 1. And of course, we expect that to be 0 or positive. So these are the 3 statistical tests. And of course, when you are writing your thesis, you have to write all of these 3 statistical tests in your work, explain each, and then go ahead to find out. So what do they mean? What do the interpretations mean? Well, we've already indicated that the phi CRS is representing the technical efficiency under the constant retention scale. If the null hypothesis is true, then it means that the CRS score and the VRS scores are the same for all the firms. And what that means is that the statistical test is going to be equal to 1. Otherwise, it's not going to be equal to 1. It's going to be less than 1. Okay. And if that is the case, then the null will be rejected when the test statistic is significantly less than 1 in this case. Significantly is important because of the bootstrap approach. Now, in order to be sure that your statistic you have is correct, okay, you have to find the critical values or later p-values. Remember, you are comparing the test statistic with a critical value, or you are comparing the p-value with a level of significance, which is the alpha. But we know that the distribution of the technology, the statistic, because remember, you are generating efficiency scores, and these efficiency scores are used to calculate the statistic. But the distribution of these efficiency scores are not known in reality. We've seen this a lot. Bootstrapping helps you to be able to, resample several by replacement and be able to now find appropriate values for that. So now you're able to now find a distribution of the scores. So what Simar and Wilson did was to evaluate the scale efficiency of the entire sample, what they call the global retention scale. Okay. So it's not just at the local level, but at the global level. Please note that apart from testing for the scale elasticity assumption, okay, this test justifies whether evaluating scale efficiency of the firm is also important. So again, you can use the global one to determine the local level one. Are there papers that have applied the Simar and Wilson test? Enormous, quite a number of them. Castellano, 2020, Fuentes, 2020, Harkos and Petro, okay, Falavigina, okay, 2018. Several of the people that you see, and of course, also our paper that we have, Nasara et al. In 2017, the one in the energy economics. Please use that one because I'll be using that one also to guide you. Okay? That has also applied and tested for the global retention scale. And of course, Totosa, Osena, and several others have done that. So I'm going to do a practical session. I wanted to mention this because this is important. The scale efficiency equals to 1 means that the constant returns to scale graph is tangent with the variable returns to scale graph. So it means that the efficiency score for the constant returns is the same efficiency score for the what? Variable returns. And so even if there is no variable returns, that section is still constant returns anyway. And so it means that variability doesn't matter. Size doesn't matter. Because when you look at the variable returns to scale graph, it is showing different sizes. IRS section, CRS section, DRS section. But at a point when the graph is tangent, the VRS graph is tangent to the CRS, constant returns is operating. So it means that size is irrelevant. It means that the firm is operating at an optimal scale size. Okay, possibly the most productive scale size. And so it does not really matter to use whatever variable returns to scale graph that you want to use. So what I'm going to do now is that we're going to look at a real data set. And like I said, this paper is in energy economics. And I'm going to just use a bit of that to show the data set and then to run the analysis. Okay, this is an applied data set. I'm going to show you the actual data sets in Excel. Okay, so let me take you to Excel and show you a bit of the data set. Okay, I hope you can see the data sets in there. Please, if you can see it, just type yes, so that I know that you can see the data set. So these are the names of all the oil companies that we selected. ADNOC, Camerada. Okay. As you go deeper, Apache, British Petroleum, Chevron, Burlington, okay, and all of the oil companies that we looked at. Okay. And the ID is indicating the names of the firms that we give to it. The year from 2001 to 2010. The input, the outputs that we use, oil produced, gas produced. The inputs, reserves, oil reserves, and then gas reserves. And then the number of workers that you have. Now, there are certain other dummy variables or categorical variables you have regarding the ownership. If that particular firm is 100% owned, it will indicate here. If it is a national oil company, okay, that OT that you have there is the ownership type. The ownership type. So whether it's a national oil company or it is an international oil company, IOC, that is indicated there. And then the other one is operational location. That is a OL. Where is it operating, the operational location? So whether it's a local firm or it's a multinational firm, you see it. If it's a local firm, it has an L. If it is a multinational firm, it has an M. Okay. In that paper, we introduced a new terminology, OTOL. So now we blend it, whether it's a local national oil company. Okay. So we are blending the two, local oil national company, or is a multinational international oil company. So this is the data. Our interest is in the input and output. Okay. So we're going to take this data set to Excel. And once we get to Excel, we are going to run this data set and then be able to come out with something as it relates to, what do you call it? Something that relates to the returns to scale at the industry level. Because the thing is that if you're able to do that test of returns to scale at the industry level, the advantage is that you will now be able to know whether you're dealing with CRS, that's what you're using, or you're not dealing with CRS, but you're rather dealing with something else. Okay. All right. So let me see what I can get us started in that regard, because all right. So I'm going to take you to the R, and then we can look at how the thing is. So this is a command number 46. This is entitled Returns to Scale via Bootstrapping Simar Wilson. The first thing to do is to require benchmarking. So if you have not installed the benchmarking, you ensure that you install it and then you have it. Okay, you install the benchmarking. And then you bring the data set from Excel to R. So what I'm going to do is I'm going to go to the data set in Excel. Now, these are basic things that I know, we all know it. Okay. I'm going to just copy the data set, come to R, okay, and just run it. So I'm going to run it here. I've run the data, and I'm just going to show the data by highlighting command number 48. So you see, it says that data DAT. I just ran the DAT. And you can see down there in the console, you will notice that all the firms are showing. All the firms are showing, all of them are showing right there. So that means that the data is loaded. I'm going to go straight to command number 50. I'm using capital XO to represent the matrix. I don't know whether I ran the benchmarking, but I don't think I did. So let me run the benchmark. Perfect, it's done. So let's create a matrix for all the inputs. Remember, the inputs are X1, X2, X3, and they are in the data set known as DAT. So I'm going to just do a row binding of the input. And so I'm going to have the number of rows to be 3. Okay. And I'm going to run that. That will be represented by X0. So X0 will be all of the inputs that you have, but they have turned the columns into rows. Okay. And then the Y0 will be all the outputs that you have, which are only 2, and you turn them into rows. So these 2 are shown down there in the column, in the console. Command number 52 will run the DEA score. Okay, it's because I've turned them into rows, I'm going to use a transpose of the inputs and the outputs. So let me just, because it's a constant returns I'm going to run. How do I know? You check the command here. You have RTS to be constant returns. So because it's a constant returns you are running, just we call it efficiency, but we add C to it to indicate that it's a constant returns. Okay. Just efficiency, and then add C to it. Let's do that. Okay. And then of course you can see the results. So when you highlight the EC, it will tell you the results for all the 478 firms. Every one of them, you have the efficiency scores that are for it. Remember, this is an input-oriented efficiency score. Okay. And so you can see that the scores are below 1. Now, if you want to get the efficiency scores and then use it for further work, you now run the capital EC, okay, which is just telling you the efficiency scores of the same thing, representing the efficiency scores for the firms. All right. You can do the same thing for the variable returns just by changing the RTS to VRS instead of CRs. You run that, and then you run the EV to represent the efficiency scores for that. Now that you've done these 2, you can go ahead and estimate your statistic number 2. Okay, we are going to do the statistic number 2, the test of returns to scale. We're going to estimate that. Okay. Now, there are some few things to note here. You can run this S2, okay, and you can look at the results if you want to. You can look at the results here. And the statistic is 0.8211076. Now, if you check the paper, okay, and you look at the column for S2, you see that that is the same statistic that we had for it. That's the test statistic. Okay. Now, the bootstrap, what it does is that it calculates the CRS and the VRS under the assumption of that the true technology is constant returns scale. You know that. And the results corresponds to the case where the CRS and the VRS are calculated for the same reference set of firms. Okay. Now, to make this happen, what we are going to do is that we're going to set the random number generator to the same state before the calls. Okay. And that is by this command, which is save.seed. Okay. Save.seed equals to sample int with a exponent. And then we set that very number, that very random number generator, we save it. And we can now indicate in a number of replications that we want to do. Now, regarding the number of replication, the Simar Wilson suggests 2,000, but because of our time, okay, I'm just going to use 100 replications. I just even hope that is going to be fast enough. So the number of replication, I'm going to use 100. So N rep means the number of replication. That's the number of bootstrap replications. Okay? Thousands of pseudo samples that you're going to collect to create a bootstrap. So the bias, the bootstrap with a constant returns, okay, the bootstrap with a constant returns is going to be run. And remember, the number of replication has to be identified. Now, we've already defined the number of replications to be 100. Okay? So that one is obviously set in there. Now, when you look down here in the console, you see that the 10 is running because the number of bootstrap replications are happening. Okay. And once you see that red symbol, what it means is that it is running. So you don't want to interrupt it. Okay. I told you that 2000 would take some bit of time. Now that's because I have a lot of things running on the computer, but if not, everything should have been fine. And you can see that it's taking some bit of time. Oh, good, we are done. Okay. Yeah. Ideally, this is not supposed to happen so long like that. You can see the number of bootstrap replicated by running this. Okay, and you can see them here, all of them. So for each frame, you get a number of bootstrap repetitions. Set the seed by saving it, and then go and run the VRS as well. So watch carefully. You will see that the VRS, okay, you will notice that we have the BV. You're running the same thing. The first one was CRS. We are running the same thing for VRS. Again, you look at the console, you see that there is a timing saying that you can stop it if you don't want the thing to be running. I want the thing to run, so keep doing that. So we run it for the VRS. Once you've done for the CRS and for the VRS, the next thing is to do something that is known as bootstrap replica. You calculate the statistic for each bootstrap replica. And how do you do that? Well, you use this command, okay, which is the BS. Now, if you look at the BS, it is a column sum of the bootstrap from the constant returns divided by the column sum of the bootstrap of the variable returns. Okay? So that is what you use that. That will give you the statistic. Okay, that will give you the, what do you call it, the critical value for the statistic. That will give you the test statistic. Okay, so because we are going to use that command, we're going to use that command to generate the critical value that we are going to get. Okay. And I'm still on the statistic number 2. Okay, not the mean of ratios, but the ratio of means. That's what we are doing here. Okay, the bootstrapping is done. So let's run this BS command. And when you run the BS command, you see, okay, the results is giving you, okay, for all of those 100 bootstraps, okay, the summary of them, the average of them. The next command, which is command number 64 here, you can find the critical value of the test statistic. Remember, any test you do, you normally calculate the test statistic, and then you check the critical value. If the test statistic is greater than the critical value, you reject the null hypothesis. Okay. Now we're going to get the critical value at a 5% level of significance, and we'll do the same thing at a 1% level of significance. Now look at the 5% level of significance. That is 0.96778. Now you can see that, you can see without a shadow of a doubt that this critical value, this critical value is greater than the test statistic. Okay, you remember the test statistic that we had? I'm just going to show you here. The test, it was 0.8 something, 82. That's it, 82. Okay, and the critical value at a 5% is what? 0.97. So it means that the test statistic is less than the critical value. But please note that in this context, this is a non-parametric test. In a parametric test, it is when it is greater than that you don't reject. So this one, we are going to make a conclusion that you cannot reject it, the null hypothesis at the 5% level of significance. Of course, you can do it at the 1% level of significance. Okay, so let's do that. This is a 1% level of significance. When you run that, you get 0.95, okay, the same way as before. All right. So let's check whether we have to reject the null. Okay. Well, let's check. How do you check? Well, it is by using this non-parametric assumption that the critical value at a 5% should be less than or equal to the test statistic. Remember, in a non-parametric test, we expect the critical value to be less than the test statistic. You expect the critical value to be less than. Okay. So using this formula, so the question now becomes, should we reject the now, is the critical value less than the test statistic? But of course you can see it here. You can see it with your naked eye in the console here that a critical value is not. But let's see whether it will tell us false. So we expect the answer to be false. Okay. And truly the answer is false down here. The critical value is not. What about a 1%? The same thing is going to be false. Okay. And so we can now make the conclusion. So the critical values, you can use the critical value, but I even want to go ahead to find the p-value. Okay. So how do you find the p-value? If you type 1 error, remember, the probability of committing a type 1 error, okay, is the alpha. So the type 1 error will give you, with this S2, with the bootstrap replicas that we had, okay, that will give you the p-value. So this command, when you type, will give you the p-value, general 1. Okay, the p-value is 0. Okay. So that means that the p-value is 0. Okay. If you want to find the p-value for the alpha level of 5%, to still be 0. Okay. So this question says that, is the type 1 error greater than the alpha level? No, because it's already 0. So because it's 0, it means that it is not greater. Okay, that's why it's false. It's not greater. 0 is not greater than 5%. And is the type 1 error less than 1%? Is the p-value less than 1%? Okay. And this one is going to say yes, true, because the p-value, which is 0, is less than that. Let's see what it says true. And it states true. So that means that our p-value is less. And normally when the p-value is less than the level of significance, in this case, whether it's 5% or 1%, when the p-value is less than the level of significance, you reject the null hypothesis at that level of significance. Okay. And so we conclude that the null hypothesis, and what's the null hypothesis? The null hypothesis says that the technology is globally CRS. We reject that null hypothesis, which means that it is variable, it's likely to be variable returns. All right. Now, this is one way you can find the returns to scale underlining the technology. But this is just for the S2. It's not for the S1. Okay. So there is a package, another package, which is called rDEA. So you got to load and invoke that rDEA. This is just to go and help us to find the statistic S1 and S3. That is the mean of ratios, and then the mean of ratios minus 1. Okay. So let's load that. Okay. When you load that, you have to indicate that the number of firms, where are they from, with the total number of observations. Okay. So let's load the total number of observations, and then we identify our inputs and outputs matrices. Okay. These are just easily done. Now, please note that this package implements the returns to scale using the ratio of the means, okay, the one less than the unity. When you check the paper by Simar Wilson, their equation 4.5 and 4.6 will indicate that. Okay. And there's a statistic there called 48 in Simar and Wilson 2011. Okay. They will test the null of CRS versus VRS. And then after that, the null of NIRS versus VRS. All right. So after you've loaded all your information, all of this information are self-explanatory here. Okay. The next command is to test for the returns to scale. Now there's a one-time thing, and it's going to give you all the results one time. Okay. So you run this, I'm calling it RTS_G. Okay. And then indicate RTS.test. And remember, the model is this very model that we are dealing with was an output-oriented model. Okay, the one that was submitted. It was an output-oriented model. The returns to scale, then H0 means indicate the null hypothesis, and you have indicated that it's constant. The BW, okay, you see the BW, we have CV. The BW deals with the bandwidth, okay, that is used as a smoothing parameter in sampling with reflection. And CV, okay, is the one you use for sampling or reflection, or sometimes you can have BWUCV. Okay? That is for cross-validation bandwidth. Or you can have the Silverman reflection method, okay, 1986. All of them are indicative of that. The next one is B. B deals with the number of bootstrap, okay, the recommended bootstrap. And the recommended one here is 100. So this particular package says just go for 100 and be free. Alpha level is the level of significance, the size of the confidence interval that you are dealing with here. So you run this command, okay? And how do you know you can see that the bootstrap here shows that it is running. That stop clock here means that it's running. Give it some time to run. And once it's finished, you can go and look at all your results. I'm telling you, the results are just incredible because it shows all of them. If you are running cost efficiency, all you're going to do is to change the model. That model, where you have output orientation, you just write cost min for cost minimization. Okay, cost min for cost minimization. And of course, that will mean that you have your W, which are the input prices as well. And you can use that to test for the cost minimization. You can test whether the technology, the cost technology frontier is exhibiting CRS or VRS. Remember I told you that sometimes it takes some time. And now it's done. You can just go and run this result here. The one there. Okay. And then you can now get to the result. Now this command will just give you all the possible statistics you can get. Okay. And I'm going to take them one by one and show you. So you just hold command number 83 like this and run only that command number 83 and you get all of the results. Remember the focus results that we are going to have here is for, what do you call it? It's for both the S1 and then the S3. Okay, that's it. The numbers that come up are the bootstrap replicas. We are not interested in that. We are interested in the final results here. So let's pick them one by one and get to know the final results. Okay. The first one is RTH. Let me go down. Okay, because the p-values are all shown here. Okay, let me just go up and show the results. Okay. Because the information is quite loaded, you need to just take your time and scroll up. All right, so let me just go quickly down and then show them. All right, so look at the first result. The first result you get is RTS, and then it gives you the W hat. Now, if you check the formula, that W hat is the 2002 test statistic. So the test statistic S1, the S1, okay, is a W hat. And in this case, the value is what? 0.7879. So you now put that one, that's a test statistic. Remember, the things you're looking for are the test statistic, the critical value at a 5%, the critical value at a 1%, the p-value at a 5%, the p-value at a 1%. Okay. So this is the W hat, the S1, the statistic number 1. Then the 48 is always the statistic number 2. That is the mean of ratios minus 1. Okay, that is the S3. That is what you have for the W48 hat. And in this case, it is minus 22,41025. If you check the paper, you see that that was the case. And then you come to the like I told you, what is next important is the p-value. So we just jump these, okay, and just go to the p-value. Scroll down. So you get to the p-value. Okay, so now this is the p-value. You have the p-value for the S1, the statistical one. And the p-value here is what? It is 1%. Okay, the p-value here is 1%. So if the p-value is 1%, when you are writing the stars, you have to indicate the stars that you are going to use for this. That means that it's not going to be 3 stars, it's going to be 2 stars. Remember, 2 stars is 1%. 3 stars is 0.1%. And then 1 star is 5%. And then you can look at the command number, the statistic S3. That's always the one having the 48. If you look at that, that one is also 1%. So again, that one will also have that double star for it. But they are all less than 5%, so they are all excellent. And then, of course, you have whether you should reject the null hypothesis or you should not reject them. So you can see that all of them are saying true, 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 which simply means that you should reject the null, true, reject the null, true, reject the null. Okay. And you will notice the critical values. Okay. So the critical value for the S1 is 0.88. The critical value for the S3, which is of level 48, is negative 0.07. So these give you the critical values. Okay. And basically, that is, of course, you can have the critical value at a 1%. Okay. So the ones I showed you here were the ones for the 5%. But if you want to do the one for the 1%, just go up there in command number 83, change the 0.05 to 0.01. So that, and I'll run the thing again, and then you get all the information you want for 1%. Okay, just as we had for 5%. Ladies and gentlemen, what I'm going to do is I'm going to show you the final results that we had for this very paper, and then that will give you a better understanding. So you can see that these are all the tests there. And when you do that correctly, you will get this beautiful table that we generated. So you can see that we have a column for the S1. I'll just show you that properly. Okay. You got a column for the S1. That's a column for the S1. So you got a column for the S1. What is happening that is not showing? Anyway, you got a column for the S1 there. You got a column for the S2. The S2 was the one we did first with benchmarking, and that one was purely 0. So you can see that the stars give it 3 stars. And all the stars have been explained. The final conclusion on the far right shows that we rejected the constant returns and then conclude that the industry is exhibiting variable returns. So this is the conclusion that we make. Based on the null hypothesis that the technology follows the CRS assumption, since the test statistic in all 3 cases are less than the critical values at both 1% and 5% level of significance, there is enough statistical basis to reject the null hypothesis of CRS. And then we can conclude that firms in the industry vary in sizes, and a model with a variable returns to scale is an appropriate deduction for this. So once you've been able to do that, you can make that beautiful conclusion for